All right, let's go ahead and get started. My name is Praveen Rokhaya. I'm the science coordinator of the core modeling and forecasting team of the Global Water Futures program. Today, it is my pleasure to welcome Dr. Maria Helena Ramos, who is going to present our webinar on the quality and value of the hydrological forecast and predictions. Dr. Ramos is a research scientist at the French National Research Institute for Agriculture, Food and Environment. She is also an occasional lecturer at the Sorbonne University, Polytech Paris, and EIVP Engineering School in Paris. She has published over 100 scientific papers and reports, organized training courses on flood forecasting to postgraduate students and professionals, as well as co-developed several games for teaching and training on the use of probabilistic predictions in hydrology. Dr. Ramos was a co-chair of the Hydrological Ensemble Prediction Experiment, also known as HEPEX, from 2014 to 2018. She is a member of the advisory board of the European and Global Flood Awareness Systems and was appointed a fellow of the ECMWF in UK in 2019. She is currently the president of the Hydrological Sciences Division of the European Geophysical Union. All right, without taking much time, I want to kick off this webinar by thanking Dr. Ramos for accepting our invitation to present in this webinar series. The webinar today is going to be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Ramos, the floor is yours.
Thank you very much. Thank you, everybody, for being there and for listening to this presentation. Thank you for the invitation. It's an honor to be here and talk to you about some of the work I have been doing on the quality and the value of hydrological forecasts and predictions. This work is mainly, I can say, coming from PhD thesis, so I would like to also acknowledge my collaborators and co-authors here. So Ioana Zalacori, that finished her PhD in 2013, Manon Casagnoli in 2020, Anthony Lemoine in 2021. And also my collaborators from my own institute, Guillaume Tirel and Vasquin Andreassian, and those from EDF, the electricity company in France, so Thomas Huyon, Joël Gaillard, Rémi Garçon, and also our colleague Amaury Thielman from Université Laval, Université de Laval, at Quebec, for their contribution in the discussion around this thematic. This work also is has been funded by some projects that have ended some years ago. So by our own institute and by EDF, but also by the European project IMPREX and also the GPI climate project AquaClue. Well, when I was preparing this presentation, I asked myself the question about forecast and predictions and why I put that on the title that I would talk about forecast and predictions. We know both are future-oriented processes. So we are looking at the future. We are using information we have now, our models, our equations, our knowledge, and projecting towards what might happen in the future. This future can be an event outcome with a more accurate prediction or more accurate forecasts, or can be an indication that something will happen, an indication of trends at more aggregated levels. So this is more or less what I was thinking by distinguishing forecasts and predictions. But in any case, either if I'm talking about something close to now, so in the next 24 hours, in the next days or weeks, or if I'm talking about something farther away in the next months or in the next decades, talking about climate predictions, in both cases, these are both user-oriented actions, user-oriented objects, let's say. We forecast, we predict because there is someone that is going to use it afterwards, which can be flood forecasting, can be reservoir management, or for other sectors, economic sectors, such as agriculture, for instance. And then when we talk about user-oriented, we think about value. It's natural to think about the value our forecasts or our predictions will have for the users. The value chain is a concept that was discussed a long time ago, some years ago, at WMO by those the group involved in the project of the high impact weather project of the World Weather Research Program. It's a 4-year flagship project of this group. And it involves meteorologists, hydrologists, but also scientists, social scientists, and scientists involved in economics. And in this project, in this idea of value chain that was, in this case, more focusing on high impact weather forecast for the next hours or days, they have developed what they call this value chain. So this is a chain that goes from observations to decisions. So this is published by Brian Golding. You can see the reference, and it involves a lot of data, a lot of data processing, a lot of modeling. So we start from our observations, we go into atmospheric modeling, environmental modeling, modeling of impacts involving social and economic models, communicating the warnings, so communicating what we have done and achieved, and then, of course, linking it to a decision that has to be made at the end, which involves a lot of psychology, a lot of economics, also in as many decisions linked to environment. I think we can even replace or put predictions, climate predictions and planning climate action inside this chain in a way that we will have probably some different dynamics, but we will have the same ups and downs around this chain. They, in their paper, they call it the 5 valleys of death. Well, quite a strong word. And what I really enjoyed when I was reading it was the sentence about describing this figure, describing how this figure represents peaks of expertise, valleys of death, and bridges of communication, and how each peak adds value to the process, but that value is also, might also be lost in each valley. And the value of warning, also warning lead time, the gain we have in anticipation can also be lost at every stage of the process. And this made me think about how this value is introduced then here. Several aspects and several steps, and with a question that we may ask, oh, maybe it's not the 5 valleys of death, but maybe the 5 valleys of value, and how we can ensure that the value I'm gaining in some ups, in some expertise, in some process, I'm not losing later. So at the end of the chain, at least, I got at least some value at the end. So we come with this question, what is a valuable forecast or a valuable prediction? There are a number of papers and very recent papers that have investigated the value of forecasts or the value of forecasting systems. So we have I just put some examples here, papers looking at the European flood warning system, papers looking at combining uncertainties along the chain of forecasting chain, papers looking at very short lead times or for longer lead times for seasonal forecasts. So I really recommend this blog post I just mentioned here from Apex. It was written by Marie-Amélie Boucher, who's going to talk with you in a week, if I remember well, and myself and Joanna about this, what we have learned on the economic value forecast. It's from 2014, but there is some references there and some more information on HIPEX that you can get from other papers that have been appearing. We have studied a lot the quality of the forecast, but much less the value of the forecasts. What we can see from the number of papers we find in the literature, or at least those that I could read, is that value can be related to different things. It can be related to an investment, like, okay, what is the benefit I get from putting more money, more time, more people working on a forecasting system? It can be related to the utility, so not to the money or to the revenues, but more is to the fact that the forecasts or the forecasting system systems are being useful or not. It can be related to benefits, economic benefits, revenues that we get from using forecasts. And there's also this idea of using the economic value of the forecasts as a tool for risk assessment. About this last one, I'd like to highlight this paper from Tim Palmer, from 20 years ago, talking about the economic value of ensemble forecasts exactly as a tool for risk assessment. So he mentions in his paper that weather forecasts are assessed differently according to being a model developer or a forecast customer. That's what you see in the picture that is displayed on the right. So the developers will look at root mean square error or of the variable, for example, here 500 hectopascals height, for instance, and the customers will look at the pounds, the euros, or the dollars, or the Canadian dollars that they saved on the other hand. So this is this two looks, the way we are going to assess if you have a good forecast or not. And according to the author, he speculates, in fact, that the picture from the 20th century and the 21st century is a little bit different, and that in the 21st century, we are linking better these two sides of the story. And this would be thanks to the amazing ensemble predictions that we've been producing for some decades now. The fact that we assess climate with probabilities, with risk frameworks, allows us to better link the quality of our forecasts with the benefits that a user can get, a customer can get from the forecasts. So the linkage would be ensured by ensemble prediction. In this paper is a speculation from the author for the 21st century. The usefulness would be achieved by this constant interaction between the developers and the customers. But still there's a question we might ask ourselves, and that's why guided me in the work I'm presenting to you here today. It's about the investments, and if all these investments we do along the chain, along the development of these forecasts, are they rewarding? We saw there are gains and losses in value. So how do I know finally at the end it was a good investment? So this question about the link between quality and value in forecasts and predictions was the question that guided me in this work. I wanted really to know if putting a lot of effort, a lot of time, a lot of PhD students in investigating the quality of our forecasts, probabilistic forecasts or deterministic forecasts, but well, it was basically following the idea that with probabilistic forecasts, we can assess these risks and the value. We were asking ourselves, putting all this time in this quality, is it rewarding afterwards in terms of value? And I really worked more on the case of hydropower sector. And I was interested on the case of reservoir-based hydropower. Then we have other variables or the impacts, and that we are going to talk about later. The hydropower sector is quite an interesting sector to work with when we work with forecasts, because they have a range of interest. They have a range of interest in variables already, so they are interested in many climate variables, plus water variables. So here I'm talking more about the water interest, the interest on the water variables, but they are interested in many climate variables, and they have different purposes, different targeting their operations that are better fitted for different forecast lead times. So at one point, they are not a user, sorry, very focused on one single application, but in a chain that goes from some hours ahead, sorry, for security or for grid balancing, for instance, between demand and the production and operations and so on, or through weeks ahead or even months ahead. for their optimization, the planning of the infrastructures, the maintenance, the new investments they may do in the future, and so on. In this context, in the context of the hydropower sector and the use of forecasts for planning, for operations, we have also here a typical case of a chain of models. So we may think a chain of models, then a chain also of value. In this chain of models, so we start by our input forecasts. Here I'm representing the stream flow forecasts that may come from precipitation forecasts, temperature forecasts, and so on, snow forecasts, and any other variables of interest. The forecasts for the energy prices. So what the interest here is to sell energy, so secure energy for the customers. So what will be this price in the future, how the demand will evolve in the future. These are things that are input into this first rectangle. And then we are gonna use that into simulation models. Maybe sometimes you have the climate prediction forecasts or the weather forecasts, the hydrological model, the reservoir storage characteristics, and then an optimization model, how we use the best the water that is coming inside the reservoir. Then we can derive our operations, it can be weekly operations, daily operations, update the system with the actual conditions when observations have come, and then update also the reservoir storage. And so we go again in the same operation. For the sector, the sector is interested in ensuring that their customers have electricity, so they produce the energy that is needed, they then distribute this energy to the customers, and they are also interested in doing that in a way that they can maximize their benefits. They can then, when the prices are low, they are going to fill their reservoirs, let's say store the water. Water is energy here, so they store the water when it's not needed, when prices are low. And then when prices are high, they might produce the energy and then supply the demand and work on their benefits. And this is a very simplified picture of how it works, because the aim, the objective here is not to explain how it works, but how we consider that in our modeling activities. And in this very schematic view of how it will work, we all understand that there is a lot of things that vary here. First, we're talking about the future, so there is uncertainty around this activity. Then we are talking about inflows to the reservoir that have some dynamics, seasonality. Sometimes you have high flows, sometimes they have low flows. Sometimes they extend for long periods of low flows, or they have very high flows that make questions about the security of also the infrastructure and so on. And we have also the variability of the prices also that we have observed, that we will have in the future, because also the demand varies. So we have more demand at some hours, at some days, at some periods of the year, and less at others. So this fluctuation also is part of the whole chain. A chain, an interest also in following the value of what we put in and what we get out of it. So this makes me come to the first study that I'm describing here today. And the first one is about the impact of quality attributes of short-term hydrological forecasts, so forecast up to 7 days ahead. And what's the impact of this on the management of hydroelectric reservoirs? So these are the 2 PhD students that developed this work. So we took a sample of catchments in France that are related or linked to reservoirs from the the main hydropower company, EDF in France. And we wanted to study these catchments and how we could evaluate the link between the quality of the forecast that we put inside the models and the value that we have afterwards. So remember, there's a chain, forecasts in, out, I will have some decisions that will translate into you producing or not energy for a certain price. So it will come into an economic benefit, a revenue. We used 4 years of data. We tried to avoid a bit the period when renewable energies entered the market in Europe. So because the prices changed a little bit. So we got this 4 years of data we had the forecasts for these 4 years, we have data for these 4 years, and then we start to plan our work. So we always start working with reality. That's what we like, hydrologists. But then we realized that there was some issues that we need to control better. So we invested in this study that is where we built a synthetic generator for hydrological forecasts over which we could control the quality of the forecasts. So we knew what was the quality of the forecast we were putting in, if they were reliable, if they were biased or not, and etc. I'll explain you later. We also used more simple optimization model, reservoir management model based on linear programming for the optimization, and a simplified context for the management with hypothetical reservoir physical parameters. So we're not using the exact same parameters, physical parameters of the actual reservoirs, but in order to be able to work with the 10 catchments we wanted to work with, we made some simplification, let's say, in terms of the parameters that we're going to use with the reservoirs. These parameters were linked to the inflows, and the inflows were actual inflows from the upstream catchment area. So we had the variability, the climate variability, the hydrological variability of each area, the actual variability that we observe. And then we wanted to separate the influence of the forecasts and the influence of the prices. So we we fixed the historic observed electricity prices for this period. We did not change it, we did not forecast it. So we could work with only the impact of hydrological forecasts in the revenues of the reservoir. So this is the paper that you can later check on HES. For the synthetic forecasts, so we built 4 big types of forecasts with different spread, let's say, from the ensemble forecasts. So the first panel A shows you the unbiased or reliable forecast. So you can see that the forecasts in gray evolve around the observation in red. Panel B shows the overestimation forecasts that are doing an overestimate. So you can see that the gray, the forecasts are higher than, systematically higher than the observations. This is produced by a specific generator that we described in the paper. Then panel C shows an underestimation. So you can see that usually we are below the observed values. It's the same period between the different panels. And panel D shows us the underdispersed forecasts. Here we have thought about how we could mimic a bit what we sometimes find in operation settings, where we overestimate low flows and we underestimate high flows. In this way, so our forecasts are more compacted, let's say. So that's why we would call underdispersed in ensemble prediction. So we build our set of forecasts for 4 years for the 10 catchments and the different types of spread based on a log normal distribution and some ensemble coupling. The details will be in the paper. So we built the sets and we said, okay, now let's see the quality of these sets to make sure that we are using forecast of controlled quality. So here you have the median bias, for instance, for these 4 types in different colors: reliable, underdispersed, underestimation, and overestimation. Different spread factors. So we are going to look more at the spread factor number 4, because the others are just tests to make sure that we are all coming from the same initialization of the generator. So on the top is just the variability among the catchments, and here on the bottom you have the median value. So we can see that the unreliable forecasts evolves around median p bias 0, so it's supposed not to have bias. Has some small little bias can be created by when we spread the ensemble created, but it evolves around the 0. And then you have the overestimation and the underestimation and underdispersion represented. The bias on overestimation are usually highest. We are working with log normal distributions, and then we are working with stream flows, so we are limited to 0 flows, but we are not limiting the upper limit of the discharge. So that represents well what we wanted to create. So we looked at the other forecast scores or other attributes of forecast quality. So here we have the pit diagram, and in the pit diagram we are going to evaluate the reliability of the ensembles created by the generator. So the reliable ensemble should be on the diagonal, as you can see in the picture, and the others will revolve either on the upper side or on the lower side, or evolve around, which is the case of the underdispersed ensembles. So each line in this picture is one of the catchments. So remember, we have 10 catchments, and this is a summary of the quality of the reliability of the ensembles generated over the 4 years. So again, we check, we produce forecasts systematically with this bias that we wanted to produce, or with good quality. And then we checked several forecast quality scores, but here I'm just showing some of them. And this is the median normalized root mean square error on the upper part, and the normalized CRPS. It's a statistical score for overall performance of our forecast, accuracy, reliability. So it looks at different aspects, and it shows us what we were expecting, of course, that we have we create bias in our forecast, so our scores become worse. And now we had checked the quality of these forecasts that we created and said, okay, now we will put these forecasts in the model and in the management model for the reservoirs, and we see what we have in terms of gain. So there is some economic value that is generated by using these forecasts in the reservoir management model. This economic gain, so we have every day a gain by producing the energy at a given price, and we sum up all these gain over the 4-year period. And then for each catchment, we have this variability that you can see on the top, and we have on the bottom panel the median value of the gain we obtain among the 10 catchments for the different systems that we used of controlled forecast quality. So here we say gain, negative gain fact, because we use the reference system as the perfect forecasting system, which means we introduce as forecast the observations. So the management model will plan the production of energy based on a forecast that is identical to what is going to be observed later. So this gives us the zero line. So we can see that by using the different other types of forecasts, when we start spreading, creating ensembles around the observations, but still reliable ensemble predictions is the yellow one. So we lose a bit, but as you can see, it's really very small. And then especially for the spread factor higher, of course, let's look at that. And then we go for the underdispersed, the underestimation, and then the overestimation that definitely in our work penalized a lot the gains of the hydropower sector. So the overestimation makes us produce in wrong hours, in wrong timing, in a way that at the end, the gain is much lower. This is the picture. So we were, at this point, we were okay. We got the link between quality and value by working with this quality controlled forecasts and by working with this reservoirs of a given size, so we could capture this, the work with the signal of the 7-day ahead forecasts, and the signal also of the weekly prices, because as you know, prices usually are higher when people are waking up and using electricity, and then lower in the middle of the day, the middle of the week, and so on. So this variability of the price along the week is captured also by the optimization model, as well as the variability of the discharge. So we get our link between the quality and the value. We said, okay, our panels, our evaluation shows that we have something, we have a link. Make forecasts, we made them worse, we deteriorate the quality of the forecasts, we also lose in revenues. But then the question, of course, is always why and how does it happen inside the models? Remember, we have a chain of models, forecasts that enter into a management of models, a management model, sorry. And inside the management model, the model tries to optimize what, when they are going to produce energy, when they are going to use the turbine, and then when is it really optimal to produce the energy. So inside the model, we have the optimization, and you wanted to know how you could understand why the overestimation was being penalized. So for instance, to understand these complex links that were occurring through the chain, we looked at the total production that we had in these different ensembles, in these different forecasts. We have the reliable forecast that produces almost the same as the reference. Remember, the reference is the observations used as forecasts. And you can see that the overestimation, the set of forecasts that overestimate the observations, they produce something very similar to the reliable forecast. Even they produce a little bit more energy, if you look at the picture, than the observations themselves. While the other two systems produce much less energy. They forecast less water, so the management model has to handle that. Well, when you look at that production, the total production is equivalent between the reliable and the overestimation set of forecasts. But when you look at the number of hours we activate the turbines in the model, we can see that then we can see the difference. So the reliable forecasts use much less hours to produce more or less the same amount of the overestimated forecasts. So then we start to understand the trouble or the problems the management model is having by the fact that he's receiving an information that is very different from what is going to be observed. The number of even producing a total production that is equivalent to the reliable, remember that the overestimation had less gain. So it's not enough to produce more electricity to increase the revenues. And it's not optimal. There's a need also to optimally place the production at the best hours. It means I will produce the energy when I have the higher price. That's what the model has in mind, the optimization model. So I answer the demand, and I am also having better revenues, higher revenues at the end. So we can see that the information, the bad quality of the forecast was posing some challenges bringing some challenges to the management of the reservoir. So I can produce a lot of energy, but not optimally, not in the best hours. And I need more hours, so I'm not optimizing really, more hours, it's not optimal really, to produce the same amount. And still, I have less revenue at the end. We also saw, of course, other variables, the type of spillage, for instance. So we can see the high value of spillage from the underestimation and the underdispersed ensemble sets, forecast sets. And they both underestimate the high flows by conception, by design. And this underestimation then creates some unexpected inflows that have to be released through the turbines, for instance, for the production, but the stock in the reservoir has to be maintained high to the low inflow forecast. So the management model, sorry, see that we have low inflows, so I have to keep my reservoir high because I have some supply coming later. Some demand, let's say, coming later, so I have to produce. But then we have unexpected inflows, so I have to release it. You cannot overflow your dam, so they release by spillage. Spillage means water that is not going to be used to produce energy, so water lost of money, let's say. We are losing money. So managing this reservoir while maintaining the high stock brings some risk for this poorly anticipating high flows, that these two systems, underestimation and underdispersed, are poorly anticipating the high flows. So we can see from these numbers that the managed model translate that into having more spillages and producing less and gaining less. Well, the second study, so this was a study on forecasted very short range. So the second study is an ongoing on our, we've just finished, and so Antonie Lehmann just finished his PhD at the beginning of this year. We were more interested in the impact of climate change projections. So now we move from forecasts to climate projections. We are leaving the area of 7-day forecasts to projections for 2050, 2028. And we were interested in doing the same, in following this a bit the same idea, not the link between quality and value, but more into creating a chain of models and evaluating how the value goes through this chain. So what's the impact of different projections in the benefits and the performance of the system. So, you know, the issues of climate change and how they can affect water and how they can affect the production of energy in the future from hydropower reservoirs that is expected to increase and to combine with other renewable energies like wind or solar energy. So this was the context of this work. So we had, again, the chain. So it's very important to have that in mind. We have climate projections we took from the Météo France portal of climate projections called DRIAS in France, 8 GCM RCMs that we had available from the historic period in up to the end of the century, 2 RCPs, so we had the 4.5 and 8.5 to create these two types of more optimistic and pessimistic of carbon pathways. And with this information, we put it on, we fed it into a hydrological model. For those who knows our models from our teams, the JR6G model, conceptual model, reservoir basin, etc. And then the discharge projections were fed into a stochastic dynamic programming model. So it's a model that can count, take explicitly into account the distribution, the probability distribution given by these projections, different members of different scenarios of the climate projections. This was a collaboration with Université Laval, I acknowledged here for this work. So here again, we are not working with prices for the future. We are not working with projections of prices. We took an average price evolution, higher in France, at least higher prices on winter when the demand for heating is higher and lower prices in summer. And we use that chain, just making variable the projections, the different projections for different periods of the future, and then seeing how it impacts the management of the reservoirs. We took 4 reservoirs this time, and this time we we approach it to the real characteristics of the reservoir in terms of size, volume, and the configuration, and so on. So we did not model exactly how it works with the complexity of users, of usages of water, and so on, but we model as close as possible to the configuration we knew, we have the numbers we had available, and the actual inflows to these reservoirs, as given by the projections, of course, and the observations. So these 4 reservoirs in France have some different regimes, but basically we have 2 that are very characteristic of pluvial regime and 2 characteristics of niveau regime. So I'm showing you these 2, Vauglin and Serponçon, in the beginning, basically because the first one has more pluvial regime, as you can see. So discharges are lower during the summertime and higher in the winter. So we have precipitation more or less over the year, and temperature higher in summertime. The bottom panels are for La Durance at Serponçon, and here you have higher temperatures also, of course, in summertime, but you can see in the discharge panel on the right that we have peaks of discharge more due to the snow melt. So May, June, you have the peak on the historic observations. So you can see here you can see from the observations in black, from the historic in gray, historic from the projections, and from 2 periods centered in 2050 and 28 for the future projections. How will these 3 variables evolve for these 2 catchments? We are going to focus mostly, well, already from these panels you can see temperatures are certain degrees higher. Precipitation is more difficult to see the differences, but we can see maybe on the rivers or on the discharge, on the stream flows, we can see especially for the catchment La Durance, which is influenced by snow, that we have lower peaks and snow melt coming earlier. So these are the difference that we found in this rounds. If we average for this catchment over these 2 periods, 2050, 28, so 30 years around these dates, and these 2 RCPs. So RCP 4.5 and the year centered in 2050 would be the more optimistic evolution. And on the other hand, the RCP 8.5 and the 28 would be the more pessimistic, so farther in the future and a worst scenario. So we can see the increase in temperature from +19, +4.6, a slight increase in precipitation, and a huge decrease in a greater, at least, decrease in discharge, notably in the more pessimistic scenario. And this is due to also the influence of temperature, and can be influenced also by the different regimes. What is the impact of this on the management of the reservoir? So we took all these climate projections, the time evolution of the projections, and we fed that into the stochastic dynamic programming management of the reservoir. Another optimization model that will look at the future. We'll try to maximize the benefits, the immediate benefits, what we can gain by producing energy now, and the future benefits also according to the climatology as they are fed in the model world. Anyway, what we observed, for instance, for illustrating with this catchment, is how the volume of the reservoir evolves in time from January and December here. So we have the result of the management model. If we use the observations as input, if you use the historic projections. So projections for the historic period, 76 until 2005, if I remember well. And then what we get if we using the model, the climate projections, they are centered in 2050 and 28. So always 30 years centered in this future periods. And here I'm just showing for RCP 8.5. So what we can see is that we change the way the reservoir, the storage in the reservoir evolves. So in a period it's higher, in another period in autumn it will be lower in the future. If we try to play also with increasing a demand for downstream water, demand for agriculture in this catchment. So this water is used for producing energy, but also they have to release water for agriculture during the summer period. So you can see here in the bottom this bell, this curve in bell. So you see that in May, June, July, August, so peak in July, August, they have to provide water for the agriculture. So this water is also used for the production of energy, but has to be produced and then sent downstream to the demand in agriculture. So what we can see that if we increase the scenarios for the future, we can see that we are going to decrease the stock in the reservoir. So we have to produce more to send this water for the agriculture. So we have, the model sees it in a different management. And this rectangle that you see here inside the graphic among July, August, beginning July and ending at the end of August, is the period of summer constraint that the reservoir has to have to be at a certain level. And as you can see, there is a conflict in the usage for agriculture and for tourism. Because if you have to release for the agriculture, you load the stock of the reservoir, and then you cannot satisfy the constraint of the tourism, for instance. So you are, in the model, you are penalized by doing that. So it reflects in the benefits. That's what we saw in these pictures. For instance, here you have the production and the benefits, how they evolve according to the month of the year for the different scenarios: historic period, a future period centered in 2050, and a future period centered in 2080 for RCP 8.5, the same catchment. So you can see at some points, at some months of the year, we can produce some very similar amount of energy, but we have lower benefits, which means we are, especially in these periods, July and August, we are being penalized because we are not answering for all the constraints in the model. Overall, if we look at all the catchments we studied, we saw a loss of annual production that was between 2 and 19–20%, and also a decrease in benefits that was of the same order of magnitude. What was interesting for us, and we are exploring more nowadays at the moment, is how this decrease in production and benefit fluctuates from the seasons. Because here the model is modeling according to what he can optimize, but of course there is also the fact that the demand may change in the future. Maybe people will ask for more electricity. We'll need more electricity in summertime because of hotter weather, and we are not taking that into account here. So my final remarks, I hope I've been time, are some reflections from doing this exercise, this studies. So first of all, to understand quality and value links, I realized that there is a real need to understand the attributes of forecast quality. What is a good forecast in terms of what? Reliability, sharpness, accuracy, and also important, how we measure that. So we use statistical scores to measure the quality. And this will tell us if it's good or not. But the model is not, the management model is not going to listen to these statistical scores. The management model is going to take the inflow time evolution of the forecast. So we need that our statistical scores reflect correctly and well the quality of our forecast and what we expect as a good forecast. The value can be more straightforward to measure, in my opinion, at least here in this context, because it's an output of the management model that's already configured to output you the benefits given the price of energy. But care is needed when we are using decisions that rely on optimization models. So there may be compensations or other influence factors, like for instance, the price that we fix it. We have not worked in changing much this price and etc. So there's some importance here of also creating systematic analysis with bias that are systematic, not every now and then, but once in a while, but systematically, so over a long time series. I think multiple uses of water and also putting humans in the loop. So I recall you, there is a very good lecture from Matteo Giuliano, Politecnico di Milano, from EGU this year that if you're interested, I really advise you to check it. So putting humans in the loop in the management of reservoirs may also review other linkages, but also other co-benefits. Maybe I'm losing in hydropower, but I'm gaining for agriculture. And in another time of the period, it will be on the other way around. There is a strong impact of future electricity prices. As I told you, we didn't work with that, but we did some analysis, some sensitive analysis, and the literature also emphasized this a lot. So, which is related to the demand, also evolution. So it's an interesting point if people wanted to study more about how handle this future climate future and water future and hydropower. And then I was asking myself, should we finally go back to the valleys of death, because finally I was more positive in thinking of value all over, but indeed we gain, we lose, and finally it's a very difficult mountain to hike. I know that saying that to Canadians is easy because all your mountains are difficult to hike, but I think that this one is quite is interesting, but it's quite hard. With this, I will finish and I will thank you for your attention.
Thank you. That was a very interesting presentation. Now we'll be moving towards the Q&A session. I'll just give a couple of minutes for people to type in their question. You can use the Q&A button that is located at the bottom of your screen. I had one question, and I see Luis has a similar question, so I'll put them both so that they have a similar type of question. So a lot of time when we talk about the quality of the forecast, we are focusing a lot of time on the base, data and base methods. But can you talk a little bit on the human factors and their impacts on the quality of the forecast? And related to that, so Luis Arnold says, thank you, Helena, for this insightful presentation. I'm wondering what your thoughts are on the role of expert knowledge and more human side of decision making within this value chain and in an increasingly automatized world.
Thank you, Luisana, for the question. I think that it's also always important to make sure that the expertise of the expert is coming at some point in the value chain where it has to be. What is difficult to evaluate, I think, is how much effort should we put into that if you want to increase our value at the end. You can do it by just because you believe in the expertise, because you know that something from an expert is better than something from a non-expert. But at the point of an economic decision, you have to say, I don't have enough resource to put everywhere. So where do I put quality in the expertise or at the end of the chain? So then these questions start to appear. I think you cannot go through an entire chain automated without this expertise popping up somewhere at one point. It will be either in the evaluation of the forecast quality or at the end in the decision that will be taken. I think that in hydrology, we are starting to try to code that. That's why I mentioned the work from Matteo. seeing that we may need to, here in the slide, you may need to understand how we can take this into account and make our hydrological or management models more flexible, not just input, I work, the model works, and give us an output, but inside this box where when the model is working, how it can be more flexible to say, okay, I may change pathways, I may change the way I'm optimizing or I'm dealing with water because I have this influence coming from somewhere, from a human side, from a decision or from just an action, for instance, it can be.
Yeah, thanks. Next question is from Martin. Hi, Maria Helena. Thanks for such an excellent presentation. It's really nice to see your work on the value of climate predictions. Building on your final remarks, I'm also interested in the value of shorter term forecasts, example of flood predictions. Here, the value of the forecast may depend on the extent to which the user responds to the forecast, where the user response depends on the risk appetite, where the value may be lower if there are many false alarms. Can you talk more about on the importance of the statistically reliable forecast, calibrated symbols on the value of the short-term forecast?
Yeah, I think that we, and I will say always this because otherwise people will kill me, but I think we should always have reliable forecasts. It's much better, and we're not going to sell our forecast saying, okay, look, I did all this model, but my forecasts are not reliable, so but you can still use it. So I think that it's absolutely important to have this reliability. How this is used in the decisions is another question. So when I started, I thought, okay, maybe flood forecasts, they don't need very reliable, they need more accurate forecasts because they look at threshold exceedance and then they say, okay, it doesn't matter if I exceed by 1 or 2 or 30, I exceeded, so emergency services in place and so on and so on. So they need some accuracy, maybe less on reliability. And I thought, well, maybe the managers of reservoirs need more reliability because they are doing that every day, not only on extremes, but every day. So it's like playing poker. You play every day, you expect to gain at the end of a year, and not gain every time, but at the end of the year and so on. But then once other operators of hydropower asked me, but is it really necessary to have reliability for us? We need more accuracy. So I think that what a user need depends a lot on how they make their decisions. If they base their decisions on accuracy, they need accurate forecasts, even if they are not reliable in terms of score. If you look at the pit diagram and you say, no, it's not a good pit, I will work 3 years more on that. But if it's accurate enough for them to make their decisions and make them useful, maybe it's already enough. So I think that's the link. Maybe we rely too much on the statistical scores of the quality, and we should more try to understand how the decision depends on quality and which attribute of forecast quality, I think. Just to make a comment on the false alarms, it's something that I think we need also to think about on the community about, should we keep on that, okay, let's not give many false alarms because otherwise people will not believe in us and so on, the boy who cried wolf and so on. But also forecasting, flood forecasting system, very short-term forecast system. The target for a short-term flood forecast, if I'm forecasting floods for tomorrow or for 48 hours, I don't want it to have misses. I understand the importance of not making false alerts, but most of all, I don't want it to see a big event coming and I didn't see it. So at some point, we focus on false alarms because we have some nice legend written about the boy and the wolf, but the flood forecast, he cannot miss an event, because miss an event means death, mean losses of life and unexpected, and that's not good. So this kind of trade-off and balances, we need to understand what is the attribute, what's the quality that makes me take a better decision.
Yeah, thanks. The next question is from Al. Any consideration on the value of data in this context? Would, as an example, in a small investment in more or improved data sets, let's consider high elevation snow data somewhat increases the overall value of the forecast and still be cost effective?
I'm reading again the question, sorry.
Yeah, no problem.
Yeah, good question. Very good question. I haven't studied this specific value of the data, except for if you see data as the forecast that inputs the hydrological, the management model. I think that in the context of the climate projections, where it was in the second study, it's much more difficult to produce controlled quality input because we don't know the observations in the future, and and there are some, in my opinion, there are some physical process that need to be better understood inside the chain. The relation with increased temperatures, for instance, more water vapor, where, when, in which season, because this is very seasonal in a large reservoir management. How seasonality will change, and so maybe going back to historic trends and the data that we can work with the different quality and check how this will impact the responses and the physical process that will be modeled by this data. And then there could be maybe a way to reduce a bit the uncertainty of the response of the management model, and maybe try to target better what would be more cost effective. I think I'm sure I was not very clear, but since it's been taped, we can listen to that.
Yeah, thanks. I don't see any more questions, and we are running a few minutes after allocated time. And just to tie into the comment that you mentioned about that we don't want to miss the flood events. So I was just wondering about the recent flood in Europe, and I was wondering, was there any prediction, like did we miss it or what happened? And tied to another question that Martin had was, what are the major problems in in recent prediction of floods in Europe?
Yeah, that's a very good question, and I think that a lot of hydrologists and meteorologists are looking at that, and also politicians. And I think it's I haven't studied these major floods, and I was not involved in the forecasting of these floods, so I cannot say more than just give an opinion. I think that it's interesting to come back to this value chain, which seems at a first look very obvious, very, of course, we have this bridges, we have this valleys, we have these steps to make, but it's interesting to have this kind of concept, or always in mind, to analyze where was a break, and or where were the different breaks. What this, I think this event will give us good lessons, and especially because it was something that affected a lot of countries in Europe. So not only Germany, but Netherlands, Zurich, Switzerland, Belgium. So we have a lot of examples. I think that we have a lot of things to learn with these events, and I hope people will come together to analyze in which point of the chain there was something that happened not very well, or where it really worked very well. In some places it really worked very well. So I think we can have use this as a very good example. I hope it will be like that in the future.
Thanks. I want to thank you for your presentation, and I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. Just a note that next week we'll be having Dr. Emily Boucher from the University of Sherbrooke, who will be highlighting how we can make the most of the models and observations for better quantification of snow. So please stay tuned. That will be all for today. Thank you again. Please stay safe. Maria, you have any final comments?
I'd just like to thank you very much, and I hope one day be able to come and see you in real life and be able to discuss more with you on all these topics. Thank you very much.
See you a good day. Bye.
Thank you. Bye-bye.